Hello, good morning. My name is Andrew Ortega, and today I will be demonstrating the usefulness and limitations of mathematics in techniques in astronomy. And first off, I will start off by first explaining the the introduction of mathematics in astronomy. Right. So, what is mathematics used in astronomy? Mathematics is used in astronomy as a mathematical science in a way, right? In other words, the quadrivium tradition, math used for measurements, modeling, and predictions. And also, my thesis statement for this presentation, which it will be that astronomy has always been considered a mathematical science in a way, right? We use mathematics in astronomy in order to measure planetary distances, in order to measure geometry in certain types of orbits, like for example the orbit of the Earth or the orbit of Jupiter, how to compare both, and also to predict the movement of celestial bodies, so where an asteroid will go, or where stars can actually explode, things like that, or for example the little movements of comets throughout the solar system throughout the universe, right? For to measure the motion and to anticipate the motion as well. My thesis for this project is that Kepler mathematical innovations significantly improve over time, right? As astronomy by making them empirical, but also in a way by making them testable, right? But the effectiveness of mathematics in a way is not at all that accurate 100%, as we'll prove it on later in the presentation, because it always depends sometimes on the assumptions, right? But also on observationals that need to be confirmed in a way. And it also occurs with limitations that appear when mathematical models have or when they exceed or contradict available data that's already present. All right. So for slide 3, I will be in showing the improvements of over preceding theories. And for here, I will show Tycho's precise measurements, which is the arc minute, and also Kepler's innovation that allow data to shape geometry. And how I will explain this. So, for example, before Kepler, the most accurate and astronomical data from Tycho Brahe, who he had measurements right that were a little bit more accurate, but often without a single arc minute, right? Sorry, not without, within a single arc minute, and they were remarkably a little bit more precise before the pre-telescopic era that they had, right? In the astronomy studies, Kepler, in a way, he improved over the precedings theories, which were not new, right? Not new models, but they were in a way new. You can say new methods that he was using, right? Instead of forcing the planets into geometric perfections and just measuring, oh, it had to be such perfect measurements to measure the orbits of planets or other things like that. He also he allowed to for data, right, to dedicate the shapes of the orbits. As I read also on Iton on Kepler, as Iton notes there on the book on page 253, Kepler discovered that the planet moves slower when it's farther away from the sun, as something that the circular models do not explain in those models, which Kepler actually noticed, right? And for slide 4, I will be showing, right, that Kepler challenged a long-standing assumption. He from the what's it called, the Ptolemy and Copernicus planets, that they must move in a more perfect circle, and which he demonstrated in his equation, which is r equals 1 plus e cos theta. He describes that orbital distance using the eccentricity, right, of e, as Wilson explains in page 20, right? This equation on represents an ellipse or a parabola or a hyperbola, right? Depending on the value of e in the equation. This shows that, for example, this shows that the mathematics also does not really force the planets to move in the ellipse, but only observations can confirm that. Observations that will not deal with measurements, will not deal with like how to measure distance or things like that. Observations for what you see, they can confirm which mathematical possibility can correspond to that nature. But like I said, a possibility, not always the assumption itself, right? For slide 5, so like I see here, slide 4, it shows the rejection of perfect circles, and also that Wilson multiple shapes possible shows multiple shapes possible, right? But does not guarantee an ellipse. So for slide number 5, Kepler really tried to show precision and predictive power that mathematics is used in astronomy. In a way, wide reduction of Mars, for example, the reduction of Mars in a 8 arc minute, right, which was a low error. The first reliable prediction of planetary positions, foundation for modern navigation and imagining, and also the way he precise mathematics in astronomy. Um, in this slide, what I was trying to, I did certain bullet points, but I will be talking the rest just so you can get an idea of why I put these bullet points here, right? And this is because Kepler was able to reduce Mars' orbital error by the 8 arc minute, right? There was a discrepancy, a large discrepancy, enough to that it, for example, it invalidated the circular models that were already in existence to under 1 argument using the ellipse. Right, this improvement created the first mathematically reliable model, right, of planetary predictions. And it also, as I stated here, Alan Chapman, he argues in one of his books, he argues that Kepler essentially uh, he mechanized a way of astronomy turning into a field of grounded grounded measurements that can be used with mathematics, with mathematical precisions, right? For example, modern satellites now they use navigation in for example in space. They decided that in space we can be able to use them for navigation, and these technologies that we're actually evolving now, they continue to rely on the same mathematics that were used back then in astronomy. So now we see why mathematics plays an important part in astronomy, because without this, the world would be different. We won't be able to actually use the internet because of the satellites of all these measurements in mathematics, right? Using in astronomy. And in the slide number 6, I will be showing the transitions in despite the strengths, right? Mathematics has its strengths within the transitions in astronomy, but it also has its weaknesses. But here is strengths is that math depends on assumptions in a way, right? Now, people can say, take it a look away like might be a weak statement. Why? Because assumptions are not always accurate. But most of the times, people base the assumptions based on the past knowledge that they have had, right? Models can exceed available evidence. That can happen too. This is one of the weaknesses that mathematics has in astronomy. And also, Kepler has shown that he has a little bit of errors and he does not state them clearly. Even though mathematics, right, for example, has revolutionized astronomy in a way, they also introduced the errors and limitations in the models. The models that often depend on idealized assumptions that are even on Kepler's own work that he even demonstrated that he has his certain contained errors due to the limitations that math has on astronomy and the measurements, for example, and the absence of later physical insights that you need for mathematics in order to prove a statement. In, for example, insights like in gravity, right? And also for uh, page number 7, right? For slide number 7, The limits in Kepler's circular theory. For example, Kepler initially he tried to fit the planets into circular orbits. However, he discovered that the radii vectors, lines from a planet to the sun did not align correctly, did not align consistently when applying the mathematics and assumptions, right? The circular assumptions that he had, they really did not apply. The famous 8 arc minute that we talked earlier ago, the 8 arc minute error showed him that even the best circular models, they could not even match Tycho's precision that he had. This actually made him a little upset, right? With this mismatch push Kepler towards the ellipses more, showing that mathematics must adopt to observational reality in order for it to be proven correctly, right? And for example, in slide number 8, as I will demonstrate here, right? The mathematics ambiguity for example, in r equals 1 plus e cosine of theta, the equation permits multiple geometries, right? That's a good thing for mathematics and astronomy. And also the ellipse only if zero is less than e and is less than 1, the observation required to choose the correct case. You have to choose the correct case in order to be able to explain it, right? As Wilson, he explained also, the formula r equals 1 plus e cos theta does not guarantee an ellipse. It doesn't guarantee it, right? But what we can do is that it can describe a parabola, it can describe a hyperbola instead, right? And this ambiguity reveals a core limitation. In mathematics, it describes also the possibilities of astronomy must determine which possibility is real, because not all of them will be real. Without observational data, the math alone cannot really decide, right? So you have to be very careful to what models to choose and what mathematics to solve when trying to solve astronomical work. In slide number 9, here it says that it depends on idealized assumptions. Like one of the main things for mathematics and astronomy is the assumptions, right? For example, the perfect spheres and vacuums do not exist. Simplifying assumptions distort nature, and also some predictions, for example, the multiverse, are unverifiable, right? For example, the astronomical models often rely on ideal conditions. Uh, for example, perfect spheres or frictionless vacuums, and also uniform motions. These simplify the equations, but they distort reality. Some modern predictions, for example, such as the models of the multiverse, they are elegant, they are a bit accurate, but they're not testable in a way, right? Which raises the question that you can ask yourself about the limits of mathematics and astronomy, right? And the reasoning that this can cause in order to prove that you do not have enough evidence. The evidence is absent in a way when you're trying to use mathematics in astronomy. And for slide number 10, which is next here, mathematics a observational of errors. It has a bit of errors, right? Kepler's residual errors, as he kept occurring all over again. The distance in measurements introduce rounding errors, right? And the modern example of that error is that the Hubble constant discrepancy. They keep having errors in a way that, for example, even Kepler in his final models that he had, he contained small little errors because he lacked a physical explanation, like the Newtonian gravity that he had. Distance calculations across light years introduce rounding errors that compound over time. A modern example that we can have here, like I said, the Hubble controversy that happened, in which different mathematical models, they produce a lack of a lack of information and based on assumptions, right, that were incompatible with the value of expansion, of cosmic expansion. So this shows. So as I was continuing, because the video had a 15-minute limit, so as I was continuing with my statement, right? They wish that the mathematical observational errors in the slide 10, in which that different mathematical models they produce more incompatible values, right? They're not as much accurate, and also they don't really show the cosmic expansion that can happen in the universe. This shows that even today, math can outpace, right, observations in a way. And also, as we move to slide number 11, here is my mathematical formula that I chose. Oh, sorry about that. It shows here something that interrupted me. For example, for slide 11, here I set a set of equations, right? So, for example, that I put here, equal areas in equal times, right? Area, the formula of area, which is a equals 1/2 r squared, triangle theta. So let me explain this in a way. I'll demonstrate a simplified proof, right, of Kepler's second law, which states that the joining of a planet and the sun sweeps out equal areas in equal times. Okay, so for example, let's get in a imagination, right? Let's imagine that a small movement of planets along the orbit, that the area is swept out. Is approximately a triangle, right? And that for example, the area is a equals 1/2 r squared triangle theta, right? And then the angular momentum, sorry, is L equals m r squared, uh, in parentheses, right? I'll put that separate so we can identify it. D theta slash dt. Okay, so solving this rate, right, at which area is swept out, we gotta ask ourselves, right? Okay, so for example, dA slash dt equals to 1/2 r squared. Okay, so now if that equals 1/2 r squared, we can know that d theta slash dt equals to L slash 2m, right? So what is m? M is the momentum. So since angular momentum is conserved, dA slash dt is constant. So this explains in a way why planets move faster near the sun and move slower farther away from the sun, right? Which this matches Tycho's data that it supports Kepler's law. So, for example, this is a way to explain that why Mars moves faster than we can say Saturn, we can say Jupiter. So, the more you are to the sun, the more faster you move, which is the pull of gravity from the pull of gravity from the sun causes these planets to move around faster, right? It's like the force of gravity. And this is the mathematical equation that I can prove of this happening in using Kepler's second law. And for my last conclusion, I will say that math gives astronomy predictive power. Models can be confirmed, right, by observations, and that also math has its limitations, driven by scientific progress, right? But as we more evolve in science, I believe that math will evolve also, and these limitations will keep deleting themselves, and they will be more accurate as times go by and as technology also improves, right? So, in conclusion, mathematics gives astronomy the ability to measure, the ability to prove, to predict, the ability to observe the motions of planets, of cosmic celestial bodies, right? And that Kepler's law shows the power of mathematical reasoning, right? The way we can reason, we can connect mathematics to astronomy, but they also reveal its limits. They also reveal that it's a lot of based on assumptions, especially when equations, right? They outrun the available data that is already available for us. right? But ultimately, astronomy is in a way more advanced than we actually have proven over time. When mathematics models and observational evidence is lacking information, so we have to scientists can work together in order to make math catch up to astronomy in order for it to be proven. Because in a way, I have this idea that mathematics was made by humans, right? And planets and cosmic celestial bodies, those are things outside our world, which is planet Earth. And we are very brave, us as humans, using our own created knowledge to measure something that is outside our world. And that's why math lacks and it outruns data because we're using something terrestrial on something that is out terrestrial, outside this world. It's like, for example, I don't know if people believe in aliens, right? But aliens using their math on us will be totally different because we don't know how their math is. So it just depends on the way math evolves and astronomy evolves over time. But math has an important part of astronomy because math is the open doors for humans to be able to learn about astronomy and to be able to predict the way things are outside the universe in human terms. All right. And so to conclude, this is my bibliography, and this is all for today. Thank you so much, and I conclude my presentation. Thank you. And this is it. Thank you so much.